Good morning. In this second unit about descriptive statistics, I'm going to talk about two-dimensional descriptive statistics. Okay, so what is a two-dimensional random variable? It is when we have two random characteristics observed or measured from each individual. And then imagine that we have two columns of data. Can we say that it can be two different things? It can be one single two-dimensional variable, or it can be two one-dimensional variables. How can we know that? Well, it depends on the example. So I'm going to discuss different possibilities. If I have the length of pieces from one supplier and another supplier, then that would be the case of two one-dimensional variables, because the first value is not paired with the second value, and so on. But another example is that X can be the height of students from Valencia and the Y can be the height of students from Madrid. So it is the same situation. It is two one-dimensional variables because every value is not paired with the next one. We don't have pairs of value. Every value corresponds to the student which is different to the other one. Okay, another example is in a married couple. I can have the height of the husband and the height of the wife. Okay, then this case is different. It is one two-dimensional variable. Why? Because every row corresponds to the married couple. So for that couple, I have two measured characteristics, the height of the husband and the height of the wife. In this case, I have pairs of values. This is the key issue to recognize that this is an example of one two-dimensional variable. Imagine another example, the time taken by an algorithm X and an algorithm Y to invert different matrices. Well, again, this is an example of one two-dimensional variable. Here, the row would be the matrix. So for every matrix in row, I have the time from one algorithm and the time from the other algorithm. So again, I have pairs of values. Okay, so now this unit will explain how to apply descriptive methods to extract information, in this case, of one two-dimensional variable. Okay, so we can apply contingency table by, or what is also called cross-tabulation. This is for the case of two-dimensional qualitative variables. And this is an example. Imagine that I have a class with 71 students, and then I have the information of those who have repeated and those who have not repeated the subject. Okay, so for example, in total I have 6 students who repeated, I have 65 students who did not repeat, and then the student according to sex can be men or women, male or female. Okay, so this is the information summarized in this table. It allows to study the relationship between the two components. Okay, then here I can provide percentages. So every time that I see percentages inside a table like this one, I have to check how they sum 100%, because there are 3 possibilities. They can sum 100% in rows, or they can sum 100% in columns, or they can sum 100% if I sum all the percentages in the table. So in this case, we can check that if I sum in rows, they sum the 100%. So we have the relative frequency of repeat conditioned to sex. Okay, so if I focus in the subset of men, 10.9% repeated the subject and 89.1% did not repeat. And if I focus on the subset of women, I have that 4% repeated the subject and 96% did not repeat the subject. Okay, so here in green, I'm representing the relative marginal frequency of repeats. Okay, so in total, I can say that 8.5% of students repeated and 91.5% did not repeat. Okay, so this is the situation. Okay, usually I say that the values that appear at the margin of the table are called marginal frequencies. the values that appear inside the table are called conditional frequencies. So we have also two types of frequencies. It can be absolute frequencies or it can be relative frequencies. Absolute means when we have the count, and relative means that it is a ratio or a percentage. Okay, so here this is the same table, but now in green I have the relative marginal frequency of sex, which means that in this example 64.8% of the students were men and 35.2% of students were women. And here again I have relative conditional frequencies, but now in this case if I sum them by columns, they sum the 100%. So the information, the interpretation is totally different. I can say that in this subset of students who repeated, 83.3% were men and 16.7% were women. And also here I have that in this subset of students who did not repeat, 63.1% were male and 36.9% were female. Okay, so the definition would be that marginal frequencies is the frequency of its value from one variable without taking into account the other, and we can say that relative conditional frequencies is the relative frequency of the value of one variable in relation to its value of the other. Okay, what happens in the case of continuous variables? Can we provide a contingency table like this? The answer is yes, but before we need to regroup the values into intervals, and this is an example. And what we have to say is that to visualize or to extract useful information from this table is not straightforward. We have to think for a while. Okay, so here we have data from students, and the data were grouped according to their height in different groups. 1, 2, 3, 4, and 5. 5 groups according to height, and also 4 groups according to the weight. So in total, we have 130 students. And then if I ask, can we say based on this information that is there any kind of relationship between the height and weight? It means when the height increases, is there a tendency also to find that the weight also tends to increase? Okay, this is called correlation. When we say correlation between two variables, means that when one increases, the other tends to increase or decrease. Okay, so is there correlation based on these metrics? Well, the answer is yes, but the information is not easy to find. Okay, so here we have a relative marginal frequency of weight. Here we have the marginal frequency of the height. Here we have in blue the relative frequency of weight conditioned to height. And relating to the question that I was saying, is there a correlation? The answer is yes, because we can find that most of values different from 0 are grouped close to the main diagonal. We can see that outside this main data we have values of 0, and here also we have values of 0. What does it mean? It means that when the height tends to increase, the weight also tends to increase, and this is why most of the values tend to follow the main diagonal. So this is the clue that provides the information. There is correlation, but obviously this is not an easy method to visualize this information from a straightforward standpoint. And also there's another problem, which is that some information is lost in the tabulation. Okay, this is a very different method. It's called a scatter plot. Here we represent the values of the weight of those same students according to the values of the height, and here very clearly we find that we have correlation, because we can see that when the height increases, the weight also tends to increase. We have an increasing trend. Okay, and also one advantage of this plot is that we can color the points according to some type of category. For example, in this case, the blue points correspond to women and the black points correspond to men, and then here we can find that we have like a mixture of two populations. and this can be seen very easily from this kind of plot. Okay, so we will say that we have positive correlation, which is moderate, and there is like a linear relationship. In this case, we can apply a regression method to make predictions, but this will be part of another subject of statistics too, the part of regression. An advantage here, as I was saying, is that points can be colored to some kind of category, and in this example the information is very clear. Also, we can think if any outlier is observed. In this case, yes, we have an outlier because we have this point which is far away from the rest of blue points, but this is like at the center of the black points. So it seems that something strange is happening in this point corresponding to woman. Okay, then how to quantify the degree of correlation between two variables? We have the covariance. The covariance is this formula. Okay, so if we have n pairs of values, so for every pair of value we put the value of x minus the average multiplied by the value of the y minus the average. We make the sum, we divide by n minus 1, and this is called covariance, where n is the number of individuals or the number of pairs of values. Okay, then let's imagine that we have a negative correlation in this case. So we have points in green. It corresponds to temperature and consumption of energy for heating. When the temperature is cold, so the consumption for heating is high. When the temperature increases and it is not so cold, so this consumption is not so high. Okay, so we can fit a regression like this, and then this is the average of the x, this is the average of the y. And then we can focus on a specific point, and then we can have that the y of this point minus the average of the y is negative, but the x value minus the average of the x is positive. So when we multiply both terms, it becomes negative. Okay, so in this sum, for all of these points, I'm summing something which is negative. And the same happens for all the points which are in this sector. Okay, so that corresponds to negative covariance. But for the few points which are here, this part, the covariance is positive, and for the few points which are here, the covariance is also positive. Then, when we make the sum for all the points, the covariance is negative. So we have the rule that when the correlation is negative, when we see a decreasing trend, then the covariance is negative. But if we have an increasing trend, we say that the correlation is positive, and then the covariance is also positive. Okay, this is the rule. So we can fit a line, and then we focus on the slope of this line. If the slope is negative, the covariance is negative. If the slope is positive, the covariance will also be positive. Okay, but there's a problem. If the covariance is minus 50, for example, can we say that the degree of correlation is weak or strong? Well, we cannot say anything at all. Okay, why not? Because the covariance depends on the units, on the scale in which the variables are measured. If I change the scale, the degree of correlation is the same, but the value of the covariance changes. Okay, so we need another parameter to measure the degree of correlation, and it is Pearson's correlation coefficient. This coefficient was developed by Pearson, so okay, sometimes it is called just the correlation coefficient, or sometimes it is called Pearson's correlation coefficient. And this is the formula. It's called R, and we divide the covariance by the product of the standard deviations. It is non-dimensional. It means that if I change the units of the covariance, this coefficient does not change. And very important, it ranges from -1 to 1, so it is limited inside this interval. Okay, so based on this range, okay, for example, if the value is close to 1, I will say that the degree of correlation is strong. If the value is close to 0, I will say that the degree of correlation is weak. And if it is something intermediate, we'll say that it is moderate. And if it is close to -1, again, I will talk about a negative strong degree of correlation. Okay, so if this coefficient is exactly 0 at the population level, I will say that there's no linear relationship between X and Y. And if this correlation is exactly 1 or -1, then there is an exact linear relationship between X and Y. And here we finish this unit about descriptive statistics, where we have talked about methods of two-dimensional descriptive statistics. Thank you for your attention.